So let's look now at the evolution of galaxies. And how we're going to do that is we're going to look at galaxies that are further away from us so we can see how they used to look in the past. So the universe right now is almost 14 billion years old. So on this timeline here, we would be towards the side at the present, and we look further away and we see galaxies as they were in the past, so a couple billion years ago. Look further away, see how galaxies used to look 7 billion years ago. Further away, see how galaxies looked 10 billion years ago. And closer and closer and closer to the beginning of time at the Big Bang. We study how galaxies change with time by looking at more distant galaxies. And we look as far away as we can, and we don't really see the beginnings of galaxy formation, because when they form, they don't have stars yet, and so we can't see them, they're too dim. But what we can tell is that galaxies all seem to have formed at about the same time, within about 1 billion years of the Big Bang. So there's not any more galaxies forming now. So in order to understand how galaxies formed, we also look at the large-scale structure in the universe. And when we look backwards in time, we notice that things were much smoother. The galaxies were distributed more smoothly. We look even further back, we can see gas distributed very smoothly. And then over time, what's happened is the universe has gotten clumpier because of gravity. So here's a weak animation showing how gravity clumps material up over time on large scales. Okay. What starts out as fairly smooth, low-density gas, the red color, ends up getting clumped up into denser knots indicated by the yellow color. So that's what gravity's been doing for billions of years. It's just pulling stuff closer together. Here is a map of the large-scale structure around us. So we are here. Our local group doesn't even really show up here. Our local group is part of the Virgo cluster, or will soon be part of the Virgo cluster. Right. And this is just a map of galaxies and their positions. Don't think of this as visible to the eye. Right. Think of this as just a map. There are places where gravity has done a good job of clumping stuff up, and the places where the gravity took it from are called voids. Here is a much more modern simulation that took supercomputers. It's called the Illustris simulation. Notice the clock down here. The different colors represent different mappings. Like maybe we're watching how the dark matter is clumping up, or watching the temperature. Now we're going to stop looking at the dark matter so much and now look at the temperature of the gas. The supernova become apparent. So galaxies are in these filaments, and where filaments meet, that's where clusters of galaxies are. Mapping where the heavy element enrichment is. back to the dark matter. You don't see as much as the filament structure anymore. Things are getting clumped up. And that's today. So we cannot watch galaxies form. So we don't have pictures of it happening. So we're going to start off with some assumptions and test them in simulations, see if they produce things that make sense. So our assumption is that the universe was filled with hydrogen and helium gas. And then that hydrogen and helium gas at some point will start to collapse due to gravity. So think of these as supernebulas, right? So here's your proto-galactic nebula. Gravity starts to collapse it. And I hope this is sounding familiar. Right? Very similar to forming stars. While it's collapsing, it should be able to start forming stars. So your globular clusters would form at this point. So globular clusters don't have a lot of metals in them. Right? That's because they were some of the first stars to form before the interstellar medium gets enriched. And once the stars form, they're going to be stuck on their orbits, and the gas will continue to collapse. So here's your globular clusters. And then your gas collapses down into a disk. It's going to heat up and spin faster. At some point, you can start forming stars in the disk, and then those stars are going to have organized orbits. What about an elliptical galaxy? We think there's two ways that you can end up with an elliptical galaxy rather than a spiral galaxy. So what if your protogalactic nebula didn't have any rotation at all? Right? So here we have your protogalactic nebula with no rotation. So it's going to collapse. It'll start to form halo stars just like it did down here. But it doesn't spin faster as it collapses because it has no spin to start with. Right? As the gas collapses even further, it doesn't ever flatten down into a disk. It'll just form more stars and collapse. And you're going to end up with a galaxy full of stars with random orbits, and it averages out to look like a ball. The second idea that we have on forming an elliptical galaxy is that maybe spiral galaxies tended to come from lower density protogalactic nebulas, and elliptical galaxies formed from higher densities. And why that matters is a lower density cloud is going to cool slower, and the high density cloud can cool faster. That might be a little bit counterintuitive. Let me explain it. If your cloud is denser, it can form stars a bit sooner. If it can form stars sooner, those stars can make carbon and oxygen and neon and magnesium sooner. And once those elements are returned to the interstellar medium, all of a sudden those nebulas can start to emit light from different atoms, and it's going to be a lot easier for the emission lines of carbon to escape through the nebulas of hydrogen. So the idea is that this galaxy will form its stars before the gas disk can form, whereas this one is going to take longer for it to cool off. So gravity is going to be slowed a little bit by gas pressure, and that's going to allow the gas to settle into a disk before the stars really form. So that's two ways in which you might make an elliptical galaxy instead of a spiral galaxy. But there's a third way: galaxy interactions. So galaxy collisions are not rare, they do happen. One galaxy collision might take 100 million years. So this collision happening right now between these two galaxies isn't complete. It's still in the process of happening, but because our lifetimes are so short, we just see this snapshot. So if we want to understand what happened in this collision and what might happen in the future, the best way for us to do it is to do a simulation in a computer. So here's a simulation of a spiral galaxy hitting a spiral galaxy. And what you do is you run many simulations, always trying to see how close you can get to reproducing the image that you're trying to explain. So let's see how well they did. What do you think? You got the two centers. You got this trail of stars that gets ripped off. That's called a tidal tail. Right? Think they did a good job? Let's keep going. In this case, we think two spiral galaxies ran into each other, and eventually we think that they will merge together and form an elliptical. This galaxy is called the Cartwheel Galaxy, and it's a real image, but it's in false color. Well, how did that one happen? Let's try some different simulations, see if we can get something that looks like that. How about a spiral galaxy getting hit with a smaller elliptical? Recreate that outer ring, recreate the central brightness. I think they did a really good job. For this one simulation that recreated that picture, there was probably hundreds that didn't. So, in a galaxy collision, you're going to disrupt the galaxies. If it was a spiral, that disk is probably going to get destroyed. Any gas or dust might end up doing star formation. When galaxies interact with each other, the nebulas will often start forming stars at a prodigious rate. The Milky Way does 1 star a year on average. These galaxies can do 100 stars per year. So a starburst galaxy can use up all of their gas and dust and then run out. So when the interaction is done with this galaxy, there's really no way for it to form a disk again. It has used up its gas and dust. Right now it's all locked in stars. These galaxies are going to be bright with blue stars during the collision, during that new star formation. But if you come back in 10 million years, 50 million years, all of the high mass stars that were formed are going to start to go supernova. And a supernova makes a hot bubble in a galaxy. And hot bubbles can overlap, and they can get even more pressure pushing out of the galaxy, expanding through the ISM. And so you can have these fountains or hot gas coming out of the galaxies. Another word for them is galactic winds, but it's really just hot gas escaping from a whole bunch of supernova. When I mentioned clusters of galaxies in the last video, I mentioned that you can have hundreds or thousands of galaxies orbiting each other. The tidal forces will rip stars and gas and dust out of the member galaxies and dump it into the center of the cluster. That tends to feed the most central galaxy there. So you can make these huge, giant elliptical galaxies at the centers of clusters. They have a very creative name, central dominant galaxies. They're absolutely huge. I really like this image because in this one centrally dominant galaxy, you can still actually see the remnants of other galaxies' cores that haven't really been truly dispersed yet and blended in. It's almost like you can tell that this galaxy ate other galaxies and it hasn't had time to finish digesting them yet. I'm going to spend a few slides going through something that your textbook skips because I think it's extra interesting. Our Milky Way galaxy is currently ripping apart 2 galaxies. So if this is the Milky Way galaxy, this is the Sagittarius dwarf galaxy, and our gravity has spaghettified it, and it's in the process of merging with us. This is completely not how it would look to the human eye. This is art. Another galaxy, the Canis Major Dwarf, is currently being spaghettified by our gravity. So the pink stars are the Canis Major Dwarf stars, and the blue stars are the Milky Way. All right, this is just a map. Trying to map out these stars around the Milky Way galaxy is really hard and really tedious. They don't differ much from the Milky Way stars, so they just blend in. You have to study the chemical composition of each star's atmosphere and look for stars that look a little bit different, look like they didn't form from the interstellar medium of the Milky Way galaxy, formed from a slightly different heavy element mixture. Here is a simulation of the Milky Way galaxy, and the Milky Way and the Andromeda galaxy are pulling each other closer and closer together. So this is an animation of their eventual collision, roughly 3-4 billion years in the future. Disks are destroyed. Tidal tails of stars are pulled out. And after a few passes, they will settle down into one big new elliptical galaxy. Statistically speaking, no star should hit another star during this process, just because stars are so small compared to the space between them. Okay. So this is art, but we're trying to imagine what it would look like from Earth while the collision is happening with Andromeda. So present day, Andromeda is a galaxy we can see in the sky. In the future, Andromeda gets closer and brighter, closer and brighter. The interaction is going to start triggering star formation in all of the nebula. Lots of bright new stars forming with all this star formation. Okay, more star formation. In this example, our solar system ends up in one of those tidal tails, so we're kind of getting thrown out away from the system, so we can look down and see the two cores of the galaxy. The two cores of the galaxies, after the star formation is done, is going to look like two elliptical balls, and over time they will merge together to create one much more massive elliptical galaxy. Don't feel sad if you're imagining the solar system getting chucked out into the tidal tails. We don't really need to be in the galaxy anymore now that we've formed. I would actually prefer to be away from this galaxy for a while, because you just formed a whole bunch of stars. Some of them are high mass, so there's going to be a lot of supernova that happen at nearly the same time. So it'd be a little dangerous down here. If you ended up too close to supernova, it could blow away Earth's atmosphere.